Hi, thanks for joining me. Today I'm going to be going over problem 1J from MAT 2023. We have the floor of x denoting the largest whole number that is less than or equal to x. So for example, the floor of minus pi is minus 4. And that's because pi is 3.14, so minus pi is minus 3.14, and the biggest integer less than or equal to minus 3.14 is minus 4. A function f of x is defined as follows. If x is between 0 and 2, then f of x equals 3/4 to the power of the floor of log base 2 of x, and otherwise f of x is just 0. So for example, f of a half is 4/3. So let's just see why that's true, because f of a half is just going to be 3/4 to the power of log base 2 of a half, or the floor of log base 2 of a half. Log base 2 of a half is minus 1, so we've got 3/4 to the power of the floor of minus 1. And now the floor of minus 1, well, that's just minus 1 because it's already an integer. And 3/4 to the minus 1 is 4/3. We want to know what is the value of the integral from 0 to 2 of f of x dx. Is it 1, 2, 3, 4, or 5? If you want to have a go at this problem, pause the video now and give it a go for yourself. And I'm going to dive straight into a solution. Okay, so the solution to this problem is quite nice and involves a couple of steps here. But before we dive into that, I'll just give some general tips for solving problems along these lines. Is whenever we have the floor function involved, that usually means that we're going to have to think about when the thing inside the floor function, in this case log base 2 of x, when that jumps between integers, what happens? So what happens when log 2x is between, let's say, 1 and 2? What about when it's between minus 1 and 0? And what happens when it's between all these other intervals as well? And the second bit of advice I'd give is whenever you're integrating a function, when that function is defined and that in its definition there's a floor function, you want to almost always sketch a graph of that function. So we're going to combine those two kind of tricks here to help us evaluate this integral. So let's start by drawing up some axes here. And we're only interested in x between 0 and 2. So we may as well only draw it for x between 0 and 2. Okay, so let's have a think about this thing inside the floor function, log base 2 of x. When is this an integer? So when is this equal to n, where n is an integer? Well, that's when x equals 2 to the power of n. And n here can also be a negative integer. So here we're going to be very, very careful about what happens when x is a power of 2. And well, what are the powers of 2 in this range here? Well, we have 2, we have 1, we have a half, we have a quarter, we have an eighth, and so on. In fact, there's infinitely many powers of 2 here because we're including n to be a negative integer as well. So we're going to have to think about what happens when we go between one power of 2 to the next. So let's start between 2 and 1 here. What does our graph look like between 2 and 1? So in this interval here. So suppose x is in this range. So x is between 1 and 2. And we're not too worried about what happens when x is exactly 1 or exactly 2 because we're integrating it. And so at particular points, it doesn't really matter what the graph is. So let's just think x is between 1 and 2. Well, then we know that log base 2 of x is between 1 and 0. And so therefore, if I do the floor of that, the floor of log base 2 of x, that's always going to be 0 in this interval. And so 3/4 to the power of 0, well, that's just 1. So my graph is going to look something like that in between 1 and 2. Okay, cool. Now we're going to look at what happens between 1 and the next power of 2. So 1 and a half here. So a half is roughly there. So what happens if x is between a half and 1? Well, log base 2 of x is between 0 and minus 1 because log base 2 of a half is minus 1 and log base 2 of 1 is 0. And so therefore the floor of log base 2 of x would just have to be minus 1. And so we have 3/4 to the power of minus 1, which is 4/3. So 4/3 is roughly there. And so our graph looks something like that in between a half and 1. Okay, cool. You can probably guess what I'm going to do next. I'm going to look at what happens between a half and a quarter. So when x is between a half and a quarter, log base 2 of x is going to be between minus 2 and minus 1 because log base 2 of a quarter is minus 2 and log base 2 of a half is minus 1. So x is somewhere between, log base 2 of x is somewhere between -2 and -1. So the floor of it is going to be -2. So I've got 3/4 to the power of -2, which is 4/3 squared, which is 16/9, which is, well, bigger than 4/3. So maybe somewhere there. And perhaps you can start to see what's going to happen is it kind of looks like a staircase going this way up, where the stairs are getting narrower and narrower. Their width is decreasing by a half each time, and it's going up, 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 and in fact we're going to have infinitely many steps to this staircase here. Okay, so we get an idea of what this picture would look like. How do we evaluate the integral from 0 to 2? Well, the integral is just the area underneath the curve, so I need to work out the area of kind of each of these rectangles here. So that rectangle plus the area of that rectangle, really poorly drawn on by myself. But these are also, gosh, these are all supposed to be rectangles, and we need to work out what their areas are. So we'll start with this first guy, the big guy. The base is 1 and the height is 1, so the area is very nicely 1. How about this second rectangle, where the base is a half and the height is 4/3, so we do a half times 4/3, which would be 2/3, is the area of that rectangle. What about this next guy? Well, the base is a quarter and the height is 16/9. So base is a quarter, height is 16/9, so that's going to be 4/9 for the next one. Let's think about what the next rectangle, which I haven't drawn in, so this one here, what would that be? Well, the base would be an 1/8, and the height, hopefully we can see the pattern with the height, is each time we're multiplying by 4/3. So 1 times 4/3 gives me 4/3. 4/3 times 4/3 gives me 16/9. The next one will be whatever 16/9 times 4/3 is. And you might ask, well, why is that the case? Well, it's because each time the floor of log base 2 of x, when we go one rectangle to the left, this floor function is reducing by 1. So each time we're reducing the power of this by 1, but remember this is 3/4, so if you take the reciprocal, you're increasing the 4/3 power by 1 each time. So what's the area of this next rectangle? Well, it's going to be an 1/8 times 4/3 times 16/9. Now, an 1/8 times 4/3 is, well, 1/6 times 16/9 is going to be 8/27. So that would be the area of the next rectangle. And you can see the pattern with the areas of the rectangles. It goes 1, 2/3, 4/9, 8/27. So we're basically just adding up this nice geometric series here, and you can see the pattern. The first term is 1 and the common ratio is 2/3, so we can use our formula. S infinity is a over 1 minus r, so this is just 1 over 1 minus 2/3, which is 1 over 1/3, which is 3. So the answer here is option C, so 3. So the integral from 0 to 2 of f of x dx is 3. I hope this solution has made sense. This looks like a really, really complicated problem when you first see it. You might start to think, maybe I need to work out the antiderivative of this function, which you definitely don't want to do. That would be a very, very ugly function to work out the antiderivative of. And then you might think, then I need to plug in the limits. You definitely don't want to do that. You want to just draw a picture and spot the pattern here. So the pattern here is once you draw a few rectangles, you start to see that their areas form a geometric series. So when you add them up, you just need to do 1 over 1 minus r. So 1 over 1/3, which is 3. And that solves our problem here. I hope you have enjoyed this solution video. If you're new to the channel, please do consider subscribing and giving this video a like as well. It helps with the algorithm. But anyway, I will leave you there. Have a lovely rest of your day, and I'll catch you in the next one.